Greetings to all the participants, and I thank Professor Krishna Reddy for the invitation, and I'm very privileged to be part of this webinar series on geoenvironmental engineering, sustainability, and resiliency. I know it's one of the very popular webinar series where many participants attend this, and it's my true privilege to be part of this webinar. Now, in the next 40-45 minutes, I'm going to talk on this topic, which is innovative and sustainable use of recyclable materials for geotechnical and pavement infrastructure. This topic is very close to me because I have been working on using recyclable materials for various geotechnical applications, almost for 20 plus years, different materials that can be applied for application purpose. Now, this topic, as the title says, is mainly focuses on the payment application, which means looking at the road network in the entire world. You can see this pictorial representation with the uh, road network length in kilometers. Very clearly, the USA, India, China are almost in the top bracket, and of course, all the other countries have significant road network in their countries. And India has about 6 million kilometers of road network. That is, the latest figure says that India has almost the largest road network at present. And for this road infrastructure, the payment section would look like this, as all of you are aware of. You have a subgrade that is overlain by subbase, base, and the asphalt surface layer. Now, in the construction of these layers, subbase, base, and asphalt, if you look at this representation, this is for a flexible payment. The amount of materials, different materials consumed for the construction of a flexible payment. Very clearly, about 87% of it is aggregate is used. Rest of it is asphalt binder, filler material, and so on. Coming to the rigid payment, you can see that the aggregate requirement is slightly lower, which is about 66%, and the other materials like cement, filler material, and others occupy the remaining portion. Now, if you look at the aggregate consumption that's going to be there in the next few years, you can see this chart that is published by OECD, the Organization for Economic Cooperation and Development, which has about 38 countries in its organization. You can see that when you compare from 2017 to 2060, you can see this part, which is light ash color, non-metallic minerals. Non-metallic minerals meaning sand, gravel, crushed stone. The consumption is going to increase almost 2.5 times. That is the case for other organizations, for example, BRICS, wherein 6 countries are part of it. You can see about 1.7 times. An increase is going to be seen from 2017 to 2060. And another representation, you can see here the global aggregate consumption in billion metric tons from 2025 to 2030. A large, significant amount of consumption is going to be there with a significant increase in the consumption from almost 58 gigatons metric tons to 80 gigametric tons. Now, I'm going to talk about the Indian scenario, and I'm sure this is the case for other countries as well. In the construction of these flexible payments or rigid payments, the aggregates, the virgin aggregates or the natural aggregates are not readily available at all project sites, especially in some parts of the country. For example, the northern India, Bihar, the eastern India, and so on. One has to have a lead distance of about 250 kilometers, which means the material has to be transported through a very large distance. to construct these pavements. Now, that is, of course, going to add to the transportation emissions and add to it the emissions because of the material processing of these aggregates. It's going to lead to a very high carbon footprint. And it is not a feasible solution in terms of both the cost of the project and also from an environmental perspective. So there are alternative solutions wherein the conventional payment can be replaced or alternatively be constructed using some amount of treatment for the aggregate layers. For example, cement treated bases, cement treated subbases are one alternative. We call it as CTB, CTSB, cement treated subbase. Or one can use the geosynthetic material, which are very common these days, as all of you are aware of, to reduce the thickness of these pavement layers. Now, what other option is, in place of these natural aggregates or virgin aggregates, we can also adopt the different recyclable materials. We have RAP, recycled asphalt pavement, recycled concrete aggregate, waste glass, crushed brick, and so on that can be that can replace the natural aggregates. Now, in this presentation, I'm going to focus on uh, two materials that I'm going to discuss. And this is a photograph of the different waste materials that can be utilized in lieu of the natural aggregates. And the presentation will focus on two recyclable materials, which are mine waste, that is combined with fly ash to act as base or subbase layer of a pavement structure. Another application is using recycled concrete aggregate, which is nothing but a product of C&D waste, construction and demolition waste, to act as a base layer. And finally, we will have some summary and conclusions from the studies that we have been doing. And these are some of the recent works that we have been working on in the last 5-6 years, I would say. And about, I think, 2-3 PhD students have worked on these topics. And I will start with the mine waste as a base material. Now, before going to the actual way of using it, let's look at the mine waste, the overburden that is going to be uh, obtained from any mining site. You can see here in this schematic, you have a ore that is at a depth within the original surface, topsoil, overburden. So this material has to be removed to extract this ore, and of course, mineral processing, metallurgical processing, and so on to recover the metal material. Now, once we remove this topsoil or the overburden soil, we have this mine waste. And this is one actual site near Hyderabad, where I come from, about 250 kilometers or 150 miles from the place I live. You can see here, this is a open cast mining site wherein the coal seam is available at about 210 meters below the ground surface. So this amount of material has to be excavated through open excavation. And then this thin coal seam has to be extracted. Then to go to the next coal seam, again, you have to extract, go on, and so on. So in the process, globally, the mining waste is about 200 plus billion tons in 2024, and it is going to increase to almost 300 plus billion tons by 2033. So, so it's very important to utilize this mine waste so that we can also meet the requirements of aggregates. Now, there are many studies that are available on stabilizing or treating the mine waste. And if you look at the studies that are listed here, most of them use what is called a sintering technique. The sintering meaning one has to heat it up at almost 1200, 1300 degrees centigrade, which is very energy intensive. And most of them do not look for pavement applications. So our objective was to use this material for pavement application and use less energy intensive in the process. So these two methodologies are adopted. One is manufacturing artificial aggregates from this mine waste and also directly treating this mine waste with fly ash and geopolymerization. Now, in both the methods, we have used this geopolymerization technique. And before we get into the details of the actual technique that we have used, a quick relook at geopolymerization. The geopolymerization process is highlighted here, wherein once the source materials, which are rich in silica and aluminum, are activated by an alkaline solution, the dissolved AlO4 and SiO4 tetrahedra combines with uh, uh, to form monomers that share one oxide atom. So it is essentially an arrangement of chains where the dissolved alumina and silica come together. They form what is called as monomers. Then the next step is to form what is called as oligomers. And then finally, we have this 3D amorphous gel, which is called as NaSH. So this is the 3D amorphous gel that we are talking about, which is going to give the strength and stiffness to the material. So it is treated mine waste with fly ash, wherein the amorphous silica and alumina is abundantly available. And the alkaline solution is typically NaOH, potassium hydroxide, or sodium silicate. In this study, we have used sodium hydroxide and sodium silicate. Now, looking at the objectives of the study, the first objective was to develop these artificial aggregates for application to pavement bases and subbases. And the second application was direct stabilization of mine OB with fly ash and geopolymerized technique. Now, in the first study, we have used the overburden soil that is near to Hyderabad region, and that is sandy type soil, sandy OB or overburden. And for the next study, we have used two materials, which is sandy OB and also clay type OB soil. Now, this is a pictorial representation of the two overburden soils that are being used. You can see here, this is OB soil 1, this is OB soil 2. This is a joint research that was conducted between IIT Hyderabad and Swinburne University in Australia. So we have also used this material from Australian coal mines so that we can also understand the effect of the material type on this geopolymerization process. So two OB soils are used, sandy type, clay type. It's clay sand. This is entirely sandy type of OB soil. Now, two fly ashes, FA1, FA2, and the alkali activators are sodium hydroxide and sodium silicate. Now, this is the general geotechnical characterization, as you can see. A few things to note. The soil classification for OB soil is SP, poorly graded sand, whereas for OB2, the Australian overburden soil is clay sand. And you can see here fly ash FA1 and FA2, the two sources, and the chemical composition is given here. Both FA1 and FA2, if you look at the chemical composition, SiO2, alumina are the major constituents, whereas the calcium oxide, CaO, is about 5 to 7%, which is less than 10%. So one can classify these fly ashes as class F fly ash. You can also see the silica alumina composition for OB1 and OB2. Now, coming to the first part of the study, wherein we look at the manufacturing of artificial aggregates for pavement base and subbase applications. Now, a few steps that needed to be taken care at the start of this work was you have a pelletizer here. You can see here in this photograph, this is a disc pelletizer, which is having a diameter of about 1 meter in diameter, and it has a collar of about 100 centimeter. And what we had to do prior to manufacturing these aggregates was to run some optimization studies. So Optimization studies, meaning for different parameters, we have what is called as mechanical parameters. What should be the rotation of this disk pelletizer? What should be the inclination? You can see it's inclined with the horizontal. What should be the inclination of this pelletizer? And what should be the optimum moisture content or liquid to solid ratio of the alkali activator that we are going to add. All these had to be optimized. And keep in mind, the moisture is a very important parameter when you form what is called as pellets or the aggregates that are going to be formed. Now, once you form the pellets or the so-called artificial aggregates, we had to do the gradation so as to meet the base layer gradation or the sub-base layer gradation. Then finally, one has to do the pavement material testing to say they are meeting or they are not meeting the requirements. So this is the general process that we have followed. Now, looking at how these pellets are formed or the artificial aggregates are formed, you can see this is a photograph of the pelletizer that we have used. So here, as I said, the moisture content plays a very important role. And we have three states that are possible. What is called as pendular state, that is A, represented as A, wherein the moisture is available at the points of contact of the particles. We have another state, what is called as funicular state. Some pores are also occupied with moisture, in addition to the moisture that is present at the points of contact. Capillary state, where all the pores are filled with moisture. Typically, we look at capillary state in order to form the pellets. And one important aspect is also the mechanical parameters, wherein as the disk pelletizer is rotated, you have what is called as a centrifugal force that is directed away from the center, and also a component of the weight that is directed towards the center. And so you have what is called as gravitational force and the centrifugal force, and it is very important to balance the two forces so that the proper pellets can be formed. So to quickly show you the how it is formed, you can see here in this small video, the material is placed along with the uh, alkali activator, and OB soil plus fly ash plus alkali activator is going to give us the pellets like shown here, and then they have to be cured. The cured sample aggregates is going to look like this. So curing was done at relatively low temperature because we don't want to use a high energy intense method. So we used only 70 degrees centigrade and we cured it for 7 days. And these are the type of aggregates that we could obtain. So now we also did number of parametric studies to come up with what should be the optimal angle of disk, also the speed of disk. 40 revolutions per minute was found to be the optimum speed of the disk, and mine will be to fly ash 50 to 50 was found to be the optimal composition. And the liquid alkali activator, which is nothing but sodium hydroxide and sodium silicate, with respect to mine OB plus fly ash, was found to be 30%, 0.3. And sodium hydroxide and sodium silicate ratio was maintained as 1. And uh, we also did the oven curing at 70 degrees centigrade for 7 days. If you look at the, once these aggregates are formed, we have to look at the pavement material properties so that we say that they satisfy the permissible limits as per standard codal provisions. This is the results for artificial aggregates: aggregate impact value, Los Angeles abrasion value, water absorption, specific gravity, and soundness value. If you look at the values, you can very clearly see that most of the values are within permissible limits. For example, aggregate impact value is 17%, much less than the 30% limiting value. One observation is the water absorption value was not meeting the requirement. And one more concern with this type of aggregates is they are very rounded particles. So we had to look at how do we handle these two aspects. For that, what we did was we had to mix it with some amount of natural aggregates. You can see this is 100% natural aggregates, and Once you add natural aggregates 10%, 20%, up to 50%, we could get water absorption value within the limiting value of 2%. You can see here, this is 50 artificial aggregate and 50 natural aggregate. And the water absorption value is this bar chart. It is about 1.8%, less than 2%. And also the angularity number for 100% artificial aggregates, the angularity number is 1, which is very low. The angularity number increased with the addition of the natural aggregates as expected, and these two uh, could be taken care in terms of the water absorption and the angularity by mixing it with some amount of natural aggregate. And again, based on the application, one may have to look at how do we look at what composition we will blend it uh, for the given application. Now, coming to because we are targeting using these aggregates for base layer and sub-base layer, we prepared a gradation. For example, these are the gradation limits satisfying the base and sub-base layers. You can see here, this is the ASTM boundary for sub-base and base material, these red dotted lines. And the gradation that we chose, which is the green color for the present study, which is lying within the limits that are set by different standards. And for that gradation, we ran the CBR value, CBR testing, and we could get a CBR value of 54% at 2.5 mm penetration and 80% at 5 mm penetration. So, and also the natural aggregates, the values were 60% and 90%. And the CBR of the manufactured aggregates that are being mm, produced in this study are close to the natural aggregates. That is one conclusion that we could make out of CBR testing. Now, looking at the MR value, again, we know that MR is one input parameter for the design of payments. So we looked at getting the resilient modulus value using the ASTO code 2T307. And these are the results from the resilient modulus testing with respect to the testing sequence for 15 cycles. And the red color, the green color shows the artificial aggregates MR value with respect to the cycle, and the black color represents for the natural aggregate. So one can see that at the end of the 15 cycle, the values are very close by for the artificial aggregate and the natural aggregate. And finally, we also did the leachate studies on these aggregates. The aggregates are prepared within the mold, and the water was allowed to leach through this aggregate material, and corresponding to each pore volume, number of cycles were done. Almost about 15 cycles were done, and one can see that the initial leachate samples exhibited slightly darker coloration, and it reduced as it became lighter with increasing number of cycles. And the permeability value was also very low. The value was about 2 times 10 power minus 7 centimeters per second, which is a very low permeability value. So there is very low chance of leachate getting and polluting the underground water, if at all. And the pH is also reduced from first cycle. It was about 11.8 to 10 for the last cycle. And we also looked at the heavy metals concentration for different cycles. And if you look at the final cycle, cycle 14, most of the metals, for example, chromium, manganese, iron, nickel, the values were within the permissible limits. However, for two metals, arsenic and cadmium, we had the values exceeding the permissible limits. Considering that the permeability is very low, possibly we may have to do some pilot studies and see how it will impact the environmental point of view. Now, summary of results from this part of the study. The optimized parameters are given here. Liquid to solid ratio was 0.3. and the concentration of the sodium hydroxide was about 10 molar solution. And the most of the mechanical and durability properties were within the limits. Blending helped improve the angularity and to reduce the water absorption. The important parameters for pavement design, CBR and resilient modulus, they were found to be in this range of 54 to 80%, which is comparable to natural aggregates. Likewise, the resilient modulus values, the maximum was 179 megapascal, and it was close to the value that we obtained for natural aggregate. So, environmental risk can also be classified as low given the low permeability of the material. So that is about manufacturing the artificial aggregates from the mine waste. Now we look at directly stabilizing the mine waste with fly ash and the geopolymer that we have looked at. You can see these are the different combinations we looked at. The uh, OB1 corresponds to the overburden soil from India, and OB2 corresponds to the one from Australia, slightly different soil type. This is sandy, this is clay sand, and different compositions of fly ash was added, and we looked at different properties. So finally, we were looking at optimizing the sodium hydroxide concentration and also looking at the properties for the optimal solution. The properties are CBR, the durability, and the resilient modulus. So these are some of the typical compaction curves. You can see here for different combinations of OB soil and fly ash, uh, from 100 OB to 100 0 to 50 50. Very clearly, with the addition of fly ash, the curves move down, meaning the dry density reduced and also an increase in the optimum moisture content. Likewise, this similar behavior for OB2 and FA2. Now, this is an interesting study, interesting result. You can see here for different combinations of OB1 and FA1, this is for OB1, which is sandy OB soil. This is for clay sand OB soil. For different fly ash contents and for different sodium hydroxide concentrations, these are the UCS value. And every country has a limiting value for stabilized bases and subbases. For example, in India, we have a value of 4.5 megapascals to be satisfied. And if we look at it, this particular combination, which is 50 OB1, 50 FA1, and corresponding to 3M and 6M were satisfying the required UCS value. So we went with, because 3M is just satisfying, we went with 6M molar solution as the sodium hydroxide solution concentration, and this as the combination. Likewise, for the other OB2, you can see that even 3 molar solution was exceeding the required 4.5 MPa. So very clearly, the type of OB soil will also dictate what should be the combination. So for the first OB soil, we are okay with 6M NaOH. For the second type of OB soil, we have to go to 3M NaOH concentration. So these are some of the CBR results with the stabilization or treatment, a significant increase in the CBR value from 38% to almost 292% for OB1, FA1, for OB2, FA2, similar type of significant increase. And to also support that the so-called Nash gels were formed, we ran the SCM analysis, and one can see that the treated materials, 50 OB1, 50 FA1 with geopolymer treated, you can see that some portions, you can see the NaSH gel that is formed, for example, this part of it. Likewise, this part of it was NaSH gel, and some undissolved fly ash wherein the reaction did not happen was also observed. Now, another important parameter that should be looked at is what is the durability of these materials. So for that, we conducted the wetting and drying cycles, 12 cycles of wetting and drying as per the standard procedure. And we looked at the weight loss. And very clearly at the end of 12 cycle, we can see that the weight loss was almost 4% or so for both OB1 and OB2, which is much less than the permissible 14% as per the codal provision. And we also looked at what is the unconfined compressive strength after wetting and drying. Interestingly, you can see UCS value increased after wetting and drying because it also helps the geopolymerized reactions to happen because you are also heating it during the drying process. So that is going to be facilitating the reactions for the so-called geopolymer reactions. So they showed a high durability against moisture and thermal exposure. And finally, we also looked at the resilient modulus values for OB1, FA1, OB2, FA2. Very clearly, the untreated and treated big jump. And the end of testing, we could see improved resilient modulus of almost 470 MPa, which is very close to what you get for stabilized pavement materials. Now, a quick summary of this part of the study. OB2, FA2 showed superior performance compared to OB1, FA1, and the weight loss from durability studies are much less than the permissible limits. The residual strength gain was noticed, about 36.5% increase for OB2, FA2, and OB1, FA1, 11.7 increase. And uh, now moving on to the other topic or the other material that we have been working on, which is recycled concrete aggregate, RCA. Which, if you look at the construction and demolition waste that is generated across the globe, you can see that a very large amount is generated. And this plot gives the generated C&D waste and also the recovery rate, which is given in yellow hashed color. Recovery rate is very low for the largest producing C&D waste countries. For example, China, which is the largest producer of construction and demolition waste, recovery rate is only 10%. India has very, very low value, which is only 3%. So it's very important to use this material instead of taking this material to landfill, an open dumping site. It can cause air, water, and soil pollution and lead to health hazards. It's very important to find applications which can help in safe disposal of this material and also meet the requirements of depleting natural aggregates. So if you look at the composition, brick masonry and concrete waste, this is a typical composition from an Indian setting. And this composition can vary based on the country, because if you look at the US, for example, the concrete waste can be of high proportion rather than only 28-30%. So it can consist of concrete, bricks, glass, plastics, metals, and so on. And the material that we used for this study is from a site nearby Hyderabad, wherein this is a processing plant where screening, crushing, washing, and sieving are the major processes that are being done. You can see different sizes of material are finally processed and produced. And then you can have the gradations as given here. They call it as 40 minus, 20 minus, 11 minus, and sand size. 4.75 minus. So these are the different grades that they produce from this plant, which is called as Ramki Construction and Demolition Waste Recycling Plant. And there are again many studies that are available that use this material. However, there are not many studies that deal with stabilizing with cement along with a secondary additive. So that was our main objective, wherein we will use recycled concrete aggregate. We treat it with a primary additive, which we took it as cement, and the secondary additive, which are stable road and microsilica. And we also looked at stabilizing this material with geosynthetics, mainly geogrids and geocells. So the objectives are to use this RCA for pavement base and sub-base applications. We looked at compressive strength, durability characteristics, different additives were used, and this is the experimental plan that we adopted. The untreated or the unbound recycled aggregates, we ran a series of tests, standard tests. Cement treated recycled aggregates, again, we with an objective of coming up with uh, the optimum content of cement, we ran a series of tests. And uh, you can see here, this is a photograph of the concrete aggregate that is being used. Again, we had to come up with a gradation that is suitable for base layer and sub-base layer. So you can see here, like previously, there are limits. The base layer gradation, sub-base layer gradation was arrived at using this material. And we looked at when we treat it with cement, these are some of the properties. Uh, Los Angeles abrasion value for was about 38%, less than 40% limiting value. Aggregate impact value, pH value, they were within the limits. Now we added different contents of cement. You can say recycled concrete aggregate with 2% cement, 3% cement, and so on to 7% cement. Our criterion was to satisfy the unconfined compressive strength, which is set as 4.5 megapascal as per the codal provision, Indian Roads Congress. So with that objective, we concluded that RCA with 7% cement content is satisfying the criterion of 4.5 megapascal. You can see here, this is for 7 days, this is for 28 days curing period. And we also ran the durability studies, wetting and drying cycles like before, and we figured out that the weight loss was much less than the set 14% value. So these are some of the results from resilient modulus testing. The RCA plus 7% cement gave a value of almost 700 MPa for 7 days and 28 days curing period. The SCM results also showed that there was in the CHS reactions that will occur because the calcium to silica ratio uh, reduced from 7 days to 28 days. It was 1.92 to 1.45 with increase in the number of days, clearly showing that the stabilization or treatment has been in place. Then we went on to, based on the resilient modulus values, we then looked at designing a pavement section. So this is one section with the non-treated RCA, and this is a section with treated RCA with 7% cement. So once you look at the mechanistic design methodology and look at coming up with the thicknesses, we we concluded that the surface base and subbase layers reduction was 42, 20, and 13% respectively. And a quick summary of this part of the work. Uh, Non-treated and cement-treated can be used for pavement base and subbase layers because they satisfy the required pavement materials with respect to the Los Angeles abrasion, aggregate impact value, and so on. So RCA plus 7% satisfies the required UCS strength and also the durability properties. And the next step, what we did was in this particular stabilization, the cement percent was 7%. So this being a relatively high value, then we looked at a more environmental friendly solution, which is to reduce the cement dosage. Can we reduce it using secondary additives? So with that objective, what we did was we used two types of uh, secondary additives. One was a patented material, which is stable road, and we used two contents of stable road additive, which is 2% and 4% by weight, and the cement content was varied from 2% to 5%. The stable road chemical composition, you can see here, CaO, silica, and alumina. These are the chemical oxide compositions. Now, for different cement and additive composition, you can see that these are the UCS values. For example, 2% cement with different additive contents, 2% additive content, 4% additive content. Likewise, for 3% cement, 4% cement, and 5% cement, you can see the UCS values plotted here. And for the criterion of 4.5 megapascal, very clearly 5% cement was satisfied with addition of 2% additive. So RCA plus 5% cement plus 2% additive was able to satisfy the 4.5 megapascal criterion for unconfined compressive strength. And the durability studies also clearly showed that the weight loss is much less than the permissible limit of 14%. In the same way, we did for cement treated RCA as base and sub-base layers. We also looked at 5% cement and 4% additive. What is the thicknesses that we will come across? So very similar thicknesses we could find for cement treated, only cement treated and cement treated and additive treated. So the thicknesses were very similar. So the same reductions with respect to non-treated RCA sections. So the summary of this first additive that we have considered, uh, 5% plus 4% additive demonstrated the required criterion for UCS value, and the MR values, resilient modulus, were also arrived at. And the reduction in thicknesses for surface, base, and sub-base layers were compared with non-treated RCA, and they were very similar to that of only cement treated. So the conclusion is instead of using a large content of cement, which is 7% cement, we can slightly reduce the content, let's say up to 5%, and then use the additive so that we can reduce the cement content and reduce the carbon footprint. That is the objective. We use the other type of additive, which is microsilica, which is essentially rich in silicon dioxide, SiO2. 70% is SiO2. This is a photograph of this additive. And a similar exercise was conducted. 2% cement, 3%, 4%, 5%, but a microsilica of 10%, 20% for each of these cement contents. And what we realized is the criterion was met for 5% cement plus 20% microsilica. So that was giving us a value higher than the required unconfined compressive strength. The durability studies also satisfied the required criterion. So this is again we designed a pavement section for cement plus microsilica additive and looked at the reduction in the thicknesses when no treatment was done. So this is the summary for cement and microsilica. I think most of it is already discussed. So 20% microsilica along with 5% cement resulted in the optimum content that is satisfying the UCS values, and also the MR value for enhance the resilient modulus value by about 14% at 17 days of curing when this additive was added. And some of these results can be seen in some of the publications that we have published recently. And you can also reach out to me if you're looking for any of these references. The final topic is the same material, the recycled concrete aggregate, can be stabilized with geosynthetic, because we are using this recycled concrete aggregate in place of natural aggregate. So the load settlement response will be not commensurate with this natural aggregate. So we can use this geosynthetic geocells or geogrids in order to have the values which are close to that of natural aggregate. So with that objective, this is the experimental setup we have, where we have prepared the pavement sections in a large test chamber. This is an actuator that can apply cyclic loading and monotonic loading. So this is the section that we have, natural aggregate or C&D recyclable material. So these are the materials that are used: subgrade material, the uh, RCA and natural aggregates. This is the natural aggregate material. This is the RCA material satisfying the gradations, and some of the properties of the materials with respect to subgrade, the maximum dry density, optimum moisture content for natural aggregates. So everything was prepared in a controlled manner. And some of the photographs during experimental testing. So you can see here, this is a geogrid. This is a geocell that was used to stabilize this RCA material. So this is interesting result. So firstly, what we did was to come up with the optimum placement depth of these geogrids, and you can look at these results. This is for the control section, which is RCA, and this is for natural aggregates. The green color is for the natural aggregates, the bearing pressure versus the settlement. And with the incorporation of geogrid, polypropylene geogrid of one type 40, for different depths, very clearly with the placement depth, the load settlement response is different as expected. And you can see that 50 to 75 depth was giving the optimal performance with respect to bearing pressure and settlement. So we selected this depth for the subsequent testing. And you can see here, this is one plot where bearing pressure versus settlement was obtained. For RCA material is the black color, and the natural aggregate is the red color. Now, for different types of polypropylene grids, 30, 30L, 40, and so on, very clearly you can see some of them, the RCA is much less than the natural aggregates. And with grids in place, it is going, in fact, uh, very close to natural aggregates or above natural aggregates as well. So the performance becomes superior than natural aggregates for certain types of grids. And we can also come up with some grids which will match the performance of natural aggregates. So uh, the RCA in conjunction with grids can perform equivalent to that of the virgin aggregate. So that is the inference that we are trying to draw here. Likewise, for different type of grids, PET geogrids, similar type of exercise was done. RCA black color, and the purple is for natural aggregates. With grids, you can see the performance is grids in RCA is getting better performance than that of natural aggregates. And one other important parameter that is very useful in design is modulus improvement factor, which is a factor for design in geosynthetic stabilized bases. So the modulus improvement factor for different type of grids, you can see here, for RCA stabilized material for different subgrade conditions, these are proposed so that one can proceed with the design. This is with respect to the cyclic loading. Very clearly, natural aggregates for number of cycles, you can see here, bearing pressure versus the settlement. This is for RCA, you can see for the number of cycles, the performance is inferior to that of natural aggregates. You can see larger settlements compared to that of natural aggregates. But once you use RCA plus geocell, geocell 1, geocell 2, geocell 3, the performance is coming close to natural aggregates, or in some cases, it's better than the natural aggregates. So it's one can always use this geosynthetics with this RCA material to get the performance very similar to that of virgin aggregates. This is another way of representation. Permanent deformation versus number of cycles for natural aggregates is here. For RCA is below. For anything above this shaded portion, within the shaded portion, or grids that are performing equivalent to that of the natural aggregates. Now, I will conclude with some overall conclusions. So, mine overburden with fly ash can be an effective solution for pavement applications through artificial aggregates that are formed. They can also do geopolymer stabilization of mine OB directly with the fly ash, and the alkali activation can also be one option. And material variability all definitely plays a role that we have seen through OB1 and OB2. And treated RCA with 7% cement content satisfies the required properties. And treated RCA with lower cement content of 5% with the addition of additive, say 4% stable road or 20% microsilica, satisfies the requirements for UCS and durability. And RCA stabilized with geogrids or geocells can provide performance equivalent to natural aggregates. And I would like to acknowledge my collaborators. As I said, the work is a joint collaboration between two universities in Australia, Swinburne University of Technology and Deakin University. So I have listed some of the collaborators whom I would like to acknowledge. Uh, and the this work is part of three PhD students. Only part of it is shown here because I wanted to cover a broader topic of using these materials, recyclable materials for payment applications. So these are some of the recent works. And of course, uh, I cannot thank less my research scholars who do all the hard work and who contributed to the lab, uh, Geomechanics Research for Infrastructure and Payments Lab. And some of the publications, feel free to look at this link. There are few other recyclable materials, shredded tires, fly ash, foundry sand that we have worked for different applications, but not presented in this work. So some interesting work can be seen in these publications listing. So with that, I thank all of you for your patient listening. And IIT Hyderabad is a great campus. I think Professor Krishna Reddy has visited us a few times, and the infrastructure facilities, the research facilities are top notch, I would say. And we have a very large graduate group, almost about 40 to 50 uh, PG scholars, postgraduate scholars. So feel free to stop by IIT Hyderabad when you are in India, or if you're around, please stop by and we can interact on anything that we had to. Thank you very much.
Yeah, thank you. Thank you so much, Professor Umashankar. It's a